Hello. During this lecture, we're going to investigate a method for finding the area of a circle. This method will involve implicit differentiation, trigonometry, and a simple Riemann integral. We'll also have to use a change of variables. Now, I'm going to focus in on the first quadrant of the circle. My representative regions are going to have area y dx, and my bounds of integration for x will go from 0 to r. Now, I've written y could be written f of x, y is a function of x. And since I'm restricting to the first quadrant, I can take the square root here and obtain a function. I wrote an equal sign here because I want you to realize that I could have just as easily proceeded with y as my variable of integration, and that integral would be absolutely symmetric to this. Now, I could proceed in this manner, but it's very difficult to evaluate the integral obtained, so I'm going to pass to what might look like a polar integration. Really, I'm just parameterizing by theta and changing variables. So I put the theta here, I can write down and each one of these equations can be differentiated implicitly to obtain expressions for dx and dy in terms of theta and d theta. And doing a change of variables, I'll have to investigate how theta behaves as x changes. As x goes from 0 to r, theta will go from pi halves to 0. And I know how x and theta are related and y and theta are related. Where dx is equal to negative r sine theta d theta. Now, the r's in this integral can come out, they're constant. The negative sign can be used to change the, flip the bounds of integration. The symmetric integral will look almost the same, but it'll have a cosine squared in it. Now the integral of sine squared and the integral of cosine squared as indefinite integrals are not obvious how to evaluate. As definite integrals, the symmetry in this situation, the fact that they're equal, allows me to add the two integrals together and obtain a new integral, which I can then evaluate. Sine squared plus cosine squared is familiar. It's the identity. Integrating over simply d theta will give me the difference between the bounds of integration. Now, this value and the fact that these two are equal and add up to it provides me a means of obtaining a value for this integral. And this result, pi r squared over 4, is what we should expect to obtain.